Good morning. Welcome again from Golden, Colorado. Pleased to introduce our fourth and final seminar speaker for the CUAHSI 2017 Fall Seminar Series. Our speaker this morning is, or this afternoon or evening, depending on your time zone, is Dr. Laura Condon. Laura is an assistant professor in the Department of Civil and Environmental Engineering at Syracuse University. Laura holds a bachelor's in science and in environmental engineering from Columbia University, and then got her master's and PhD in hydrologic science and engineering from the Colorado School of Mines. Pretty quickly after that, she transitioned to Syracuse and to life as a faculty member. Laura is going to be talking today about some work that she's been heading up for Continental U.S. Integrated hydrologic modeling, so high resolution, large extent, including some anthropogenic effects. And as always, please chat your questions to me. They'll show up. I'll hold the questions till the end of the presentation, and then I'll moderate the questions as usual. And of course, we are recording this broadcast for viewing afterwards for those who couldn't make the presentation. So let's thank Laura, our last speaker, and then I'll turn it over to her. We're ready to clap.
All right, thank you for the introduction, Reed. I'm excited to be here, well, virtually here, and this has been a really interesting webinar series so far, so happy to be a part of it. So I'm going to be talking about groundwater, surface water interactions across the continental U.S. Using the model that we've been working on. So, oh, hold on, I have to get my, I guess I have to click. There we go. So I think that I don't really need to motivate this talk too much in the context of this webinar. If you heard Mark Bierken's talk, I think he gave a really great summary of advances in large-scale modeling. I think as a community we recognize that we really need to figure out how we can improve our representations of terrestrial hydrology for global simulations in order to answer the really large-scale challenges that we're facing. And for my talk specifically, I'm going to be focusing on groundwater processes and groundwater surface water interactions, because I think there's been a lot of advancement in other global modeling approaches, but from the terrestrial hydrology perspective, that's one area where we really still have a significant gap. And I think we have a significant gap, especially in considering these processes mechanistically. So this is just a quote from a paper in the WRR 50th anniversary issue by Martin Clark et al., noting that we have really a critical need to figure out how we can represent processes mechanistically, not empirically, so that we can do a better job of predicting future water cycle changes to all of the complex interactions that we're expecting. So I'm going to be talking about integrated hydrologic models where we really focus on answering these questions mechanistically. Of course, also we have issues of scale to think about. So when we're talking about answering questions globally, we still need to maintain pretty high resolution. Of course, high resolution is a relative term, so it matters who you're talking to, but this is just a plot showing a range of scales that decision makers care about, just as an example for the continental U.S. thinking about agricultural decision making, which of course is strongly tied to water resources. So if you think about the crop scale, we can be at the meter scale or the sub-meter scale. For things like irrigation decision making, if you're turning on and off a center pivot, the average center pivot is about 500 square meters. In the U.S., the average farm size is about 2 square kilometers. So these are all pretty high resolution. At the global scale, less than a kilometer resolution counts as hyper resolution. So hyper resolution decision making for individual water managers, but then we also have that in the context of these really large water systems. So for example, the Central Valley is 47,000 square kilometers. That's a really heavily engineered system where we are legitimately moving water all across that system from the north to the south. Also, you can think about our major aquifer systems. For example, the Ogallala Aquifer is about 450,000 square kilometers, and all the way up to the size of our country, which is about 8 million square kilometers. So it's a really big challenge to figure out how we can provide information that is at a high enough resolution to be useful for decision makers, but also across these really large systems that we're managing and that we know we're going to see interactions across. And along the bottom here, I've just added some bars just showing some examples of the types of tools we have and highlighting the fact that we really do have some spatial gaps, especially if you're thinking about groundwater. The observations that we generally have available to us are things like groundwater wells, which are basically point measurements with pretty small aerial coverage, and also not perfect coverage across the U.S. We generally have well observations where we're doing things like pumping groundwater. Conversely, we can get really great spatial coverage with something like GRACE, but the spatial resolution is really the limiting factor there if you're trying to use that for decision making. So integrated modeling is really one way that we can start to bridge that gap. And so far, we have a lot of high-resolution watershed scale models that don't quite get up to the extent of something like the Continental US, or we have global water balance models, which are, of course, covering the whole globe, but then are also have a trade-off for the spatial resolution. So the challenge is to see if we can figure out how to build models that can really bridge these scaling gaps in our observations. So obviously, from the title of my talk and the fact that I'm participating in this webinar series, I think that integrated hydrologic models are a feasible way that we can bridge some of these gaps and try to improve our understanding of hydrology in diverse settings. So for the results I'm going to be talking about today, I'm using ParFlow, which is an integrated hydrologic model. There are other integrated hydrologic models like this. The idea of most of these models is that we're solving physically based groundwater surface water flows. So we have 3D variably saturated flow, which we're simulating using Richard's equation, and then we have that fully integrated with overland flow. So we're basically simulating the whole subsurface, looking at gradients in head, which are driving flow, and we can have things like recharge at the land surface that leads to infiltration, and we have lateral groundwater flow and convergence to surface water bodies. We can also have overland flow, and we're solving this all within the same system. I'm going to be talking about ParFlow coupled to CLM. So ParFlow solves the groundwater surface water system, but it's also coupled to a land surface model. So and when we couple to CLM, then we have root zone and vegetative processes added, and this allows us to solve the full water energy balance at the land surface. So we're still inputting atmospheric forcings. It's not an atmospheric model, but we all are simulating energy in this case too. So just to put this in context, because it's always hard to tell what's what in modeling, everybody has different approaches. So you can think about like a lumped parameter model, which is pretty commonly used, especially in water management or in really large-scale approaches where computational demand is really a premium, where we end up treating things more like buckets that we're exchanging water between, especially if you're thinking about the groundwater. Oftentimes we treat that as like a storage reservoir that we just move things in and out of. The next level of complexity from the groundwater perspective would be like a land surface model. So land surface models are generally simulating the soil and sometimes have deeper groundwater reservoirs too, but are really simulating things as columns. So vertical exchanges are occurring, but we don't have lateral flow. So the big advantage of moving to an integrated model is that we get infiltration and lateral subsurface flow. Of course, though, if you'll note, the bottom of that arrow has computational demand increasing. So you pay a price for solving 3D variably saturated flow, and so we have to be really thoughtful about why we're doing it and how we're using this to answer questions, and really pay a lot of attention to computational efficiency with these types of approaches. So just to kind of highlight what the advantages are of this approach, so on the lower left, I'm showing that we're simulating variably saturated flow throughout the whole subsurface, so we never specify like what's the vadose zone, what's the groundwater. We just say this is the subsurface, and we solve the same equation everywhere. We have our land energy fluxes, which are controlled by soil moisture and atmospheric variables, so they're fully connected with our subsurface. And then also a big difference is for overland flow, we never specify like here's our river network and route things through our river network separately. We have water ponding occur and overland flow occur based on the physical equations that we're solving. We form water bodies within our model without a priori specifying where they will be. So this approach is really useful if you want to assess dynamic groundwater-surface water interactions. So on the left, I'm just showing a figure from Collette and Maxwell illustrating how you can have connections between groundwater depth, soil moisture, and land energy fluxes. And this is a function of how deep your water table is. It will depend on your groundwater configuration. So something like Parflow CLM, where we've connected things from the groundwater through the top of the canopy, we can really capture these connections. Similarly, another important thing that you can see with something like Parflow is that we can have groundwater convergence across multiple spatial scales, so we can have local and regional flow paths that are supporting our surface water bodies, and we can have lateral redistribution of moisture within the subsurface. Okay, so that's generally the modeling approach for Parflow CLM. I'm going to focus for today on what we've been doing to build a model of the Continental US and show you basically what we've done to validate this model and some of the scientific findings we've generated with it and where we're going moving forward. So this is just a general roadmap of where we started and where we're going. So as with other groundwater models, the first thing you need is to initialize your model, spin it up with a steady state simulation. So we have a steady state Parflow CLM simulation. Along the bottom, I'm just showing you the processes we're capturing. So that's just our subsurface and overland flow. Then we built upon this to couple it with CLM and run transient simulation. So now capturing vegetation dynamics and moving up to the boundary layer. And in the future, we'll be working to couple this up to atmospheric models. So we're simulating everything from the bedrock through the atmosphere. Okay, so first just talking about the steady state simulation. I'll go through this one pretty quickly, but this is our domain. It's about 6 million square kilometers, and we're at 1 kilometer resolution. And you can see here, I've just highlighted in blue, even though this isn't the entire continental US, we are covering the majority of 8 major river basins. To parameterize this model, we need vegetation cover, and then we have all of the properties for each of our vegetation types for the CLM model. We also have soil units that we get from the USGS and geologic units from Gleason et al. And I'll just put a little note here that obtaining the properties for the subsurface is a really significant challenge at these scales, and this is an area where I think there's a lot of activity to try to get better data sets for the subsurface, because if we need data sets that are going to cover really large spatial areas, it takes a lot to build those data sets, and so that's definitely one of the limiting factors, but luckily we do have some data sets already existing that we can use. Okay, so then after we get all of our inputs to our model, we generated a steady state simulation using just long-term average precipitation minus evaporation. So we just rain on our model for a really long time until we get a steady state simulation. And this is what it looks like. So you can see here's our groundwater configuration. The point of these little zoom in boxes is just to show you that we get a lot of spatial variability that you might not see when you're all zoomed out, that we get groundwater convergence occurring across multiple spatial scales. And if you look at the stream networks that we get reasonable stream networks coming out of this. I'll just note again that we didn't ever specify what our stream network would be. We specified our topography, which of course controls where the streams will be, and then our streams formed in the process of our spin-up. Okay, so using the steady state simulation as a starting point, then we turn on the land surface model to do transient simulations. And for this, we're doing a simulation of water year 1985. This is a pre-development simulation, meaning that we don't have any of the human water management activities occurring in it, but it is observed meteorology. So we take historical observed meteorology, put that into our model, and then we get gridded hourly outputs for about 17 variables which fully define water and energy fluxes from the subsurface through the land surface. And I'll just pause here and note that this is a really computationally and data intensive problem. So Parflow is designed to run really efficiently in parallel, so we can actually still accomplish these types of simulations, but it does still take about 500,000 core hours to run 1 year of simulation. We're running this simulation on 2,000 cores. Parflow can scale efficiently out to many more cores than this, but for the size of this problem, we run on 2,000 cores, and we can get this done in about 1 week of wall clock time. This is also a big data challenge, so we have about 3 terabytes of input for all of our climate forcings and the inputs to our model, but we generate about 13 terabytes of output for just 1 year of simulation. Of course, we can still get a lot of information. We can summarize this output and deal with much smaller outputs. We can get that down to about 200 gigabytes for just like daily and monthly data, but if you really want to look at all the hourly output, which is one of the reasons why we're running it hourly, then you have a lot of data to handle. Okay, so I'll see if video will work. Okay, so this is what comes out. This is our latent heat flux simulation, just showing you. Oh, it might pause on us. Okay, well, I'll skip the video, but oh, there we go. So we have a video just showing what the latent heat flux looks like through the year. So this is a water year, October through September. So you can see, obviously, a lot of temporal variability, and then, of course, seasonal patterns, all sorts of spatial variability going on. And I'll see if I can get the water table one to go. Nope. Okay, I'll skip the water table one. You can see something similar for the variability in water table depth. So obviously that looks really cool. You can take 3 terabytes of input, have a nonlinear equation, you're going to get something out. You can make cool videos. It looks great. The question, though, is, you know, does it make sense what we're getting out of this? Is it useful? What are the questions we can answer with it? Where are we doing a good job? Where are we not doing such a good job? So for that, we've done a lot of work to validate this model and to try to really understand not is it a right model or a wrong model, but to say, okay, you know, we're working to try to make these models better. What are the biggest areas that we need to improve? So we looked at things like biases in the inputs to our model, so biases in climate forcings, uncertainty in the parameters. I already mentioned uncertainty in the subsurface is a big factor. The fact that we're doing a predevelopment simulation, so we have no water management activities. The fact that, of course, we know we're still simplifying the physics, even though we're trying to take a more intense physical approach. Of course, we're missing things, and are we missing processes that need to be in there? And again, also the same thing with spatial discretization. So we're at a high resolution with 1 kilometer resolution, but of course, if you're thinking about like hill slope processes, that's a really coarse resolution. So we validated our model with all available observations for the water year 1985. So we have about 378 SNOTEL stations, 3,000 USGS gauges, 29,000 USGS wells. If you look at these in time, that gives us about 1.2 million total comparison points, which sounds like a lot, but if you have 13 terabytes of output, this is really a sparse observation network. So I'm just going to show you some of the results from our validation. So this is showing comparison for stream flow, for daily stream flow at 3,000 USGS gauges, and we compared the shape of the hydrograph and the total volumetric bias in the hydrograph, so we can group stream gauges where we're getting the right shape and the right volume versus if we're getting the wrong shape or the wrong volume, because if we're getting the shape wrong versus getting the volume wrong, those are really indicating different issues with the model that we might want to address. So here's a map of the stream gauge categories for the domain. So you can see we're actually doing really well in a lot of areas of the domain, especially considering the fact that this is not a calibrated model. But of course there are areas where we're not doing as well. So for example, like across the Great Plains, we have a lot of issues with bias, which actually makes sense given the fact that this is a pre-development simulation, so we're not including all of the groundwater depletions and agriculture that's happening in that area. I can show you just a couple of examples. I'll start with a good one, but I'll also show you a bad one, so I'm not just cherry picking. So we have daily hydrographs for any of these gauges that we've compared. We have 3,000 of them that we can look through. So the blue is par flow, the black is the gauge. So here's the Snake River below Ice Harbor Dam, and you can see that we do a pretty good job of matching this gauge. Conversely, if we look at like the Colorado River at Lee's Ferry, the gauge is pretty much a flat line from November to March due to hydropower and the fact that this is a really heavily managed system. And of course, in our model, we're not managing it, so we don't see that behavior in our model. So this is an example of where we know that we're getting the wrong answer, but we know why we're getting the wrong answer, or not even the wrong answer if we're trying to get natural conditions versus managed conditions. Okay, we can also look at the snowpack. So on the left, I'm showing the bias in our simulated SWE. So you can see that we're underestimating the SWE in this simulation, but also this is pretty consistent. We can attribute this mostly to a bias in the precipitation in our NLDAS forcing. So on the right, you can see the bias in our precipitation, and that these really line up pretty well. So this is also a function of the resolution of our forcing data set. This is the results for our groundwater levels. So you can see in purple are places where our par flow simulation has a shallower water table than what's observed in wells. And this actually makes a lot of sense too. If you look, the map at the right are the major aquifers in the US. So first of all, you can see that the wells that we're observing are really concentrated in these major aquifers where we know people are pumping. And second of all, where we know there's been a lot of groundwater depletion, and we are overestimating the water table depth because we have a pre-development simulation. Finally, these are maps showing comparisons for latent heat flux. So here we're using reanalysis data to compare to because we don't have enough observations for water year 1985. But what you can see is we're really getting the spatial pattern pretty well with our simulation. So there's a lot of things that you could say out of our model validation. Really the main takeaways I would say is that we can see with our existing model that we can already generate realistic behavior, but that we know that data is a limiting factor and that we have to keep improving all of the input data sets for these models as we're improving the models if we're really going to get to where we want to be. Of course, anthropogenic impacts are important, and we're working to add those in. And again, like I've been stressing throughout this, that comparing to observations can really help inform what we need to do as we're moving forward with developing these models. Okay, so assuming that you are comfortable with the model now that it's validated, we've also used this as a tool to answer science questions, which is really the main goal, of course. So we've used our results to look at spatial patterns and drivers in groundwater interactions just from our steady state groundwater configuration. We've also added particle tracking to look at groundwater residence times across scales. In the interest of time, I'm not going to talk about either of those two, but I'm going to focus on the last two. So first I'm going to talk about some work we've done to look at the impacts of lateral groundwater flow on surface water partitioning, and then I'm going to talk about human impacts. So for surface water partitioning, I'm going to talk about partitioning of overland flow, and first I'm going to talk about transpiration partitioning. So this is just a figure showing basically a disconnect we have between observations of transpiration partitioning and what really large-scale models are getting. So even though ET is the largest terrestrial water flux, we still actually have a lot of questions about it at large scales, and specifically understanding the portion of total evapotranspiration that is transpiration. So on the top of this figure, you can see stand scale estimates and global estimates of what the transpiration partitioning should be based on isotopic methods, and that gets to an average of about 62%. But if you look in the bottom of this figure, you'll see that most of the GCMs are actually getting much smaller numbers. So one of the first questions that we had was, if we look at transpiration partitioning in our model, which is really focused on improving the representation of terrestrial hydrology, where would our results fall, and would we get a more realistic representation of the transpiration portion of ET. So these are our results. And so what you can see along the top are the global isotopic estimates and then the stand scale estimates. And then on the bottom, I have histograms of our results. So you can see that we're actually doing a pretty good job of matching the isotopic estimates, and we don't have this systematic underestimation that we see with some of the other models. So I think what's really interesting about this, though, is because we are using a numerical model where we can control everything and we can see everything that we're doing, hopefully, that we can start to try to tease out exactly why we see a difference between other models and what within our model is causing this, so that we can generate hypotheses that can be further tested. So what we did is we had our first simulation that I'm showing you here, then we created a second simulation where we changed our bottom boundary to have a free drainage boundary condition, so that we would just have vertical flow, so basically taking out all of the lateral groundwater flow in our simulation. And when we do that, you can see that it significantly shifts the transpiration fraction. So without lateral flow, the transpiration fraction is 48%, and with lateral flow, it's 61%. So this indicates that it was the lateral redistribution of water in the subsurface that was really driving our estimation of transpiration partitioning. We can also look into this further and see what the mechanisms are for this. So here's a plot. These are plots showing latent heat flux, transpiration, evap, and then the transpiration fraction versus water table depth. And these plots have a lot on them. These are, every point is a grid cell in the model, so we could break this out and you could see things for, right now they're colored by soil type, but we could also break them out by land cover type or elevation or all sorts of things. But basically the point of this is to show you that for both latent heat flux and transpiration, we see a logistic relationship with water table depth, which has been well documented with other studies. But with the transpiration fraction, we actually see a peak. And this is caused by the fact that within our model, at least, we have transpiration is sensitive to water table depth at deeper depths than evaporation. So when you're basically dividing these two logistic curves, this creates a peak. Basically the point of this is to show that within our model, first of all, we can do a better job of matching the transpiration fractions, but also that we can basically dig down in and see what the mechanisms are that are causing this and help generate hypotheses that we can start to compare to other models and drive observations to see, okay, is this why you're getting a different answer or not? So I'll also talk about overland flow partitioning. So this is a Boudico plot, and basically the Boudico framework, if you're not familiar with it, the idea is that if you think about the fraction of ET that leaves a basin, if you think about a basin where you assume there are no storage changes, so all precipitation leaves as either runoff or ET, that the fraction of the precipitation that leaves as ET will be related to the aridity of the basin, so the potential evaporation divided by precipitation. And there are physical limits to this, so in an energy limited system, the maximum ET that you can have is the potential ET. In a water limited system, the maximum ET you can have is the total precip that comes in. And Boudico showed that if you look at this for really large basins greater than 100,000 square kilometers over long time periods where the no storage assumption is more valid, that the relationship between ET and aridity follows this really predictable curve. And that's really useful because it indicates that if you had things like precipitation and runoff, which are easier to measure, you could make estimates for ET. Since Boudico's original work, though, which had everything just on one curve, there's been a lot of analysis looking at the scatter as we look at smaller basins or shorter time periods, and showing that actually there's different locations can fall on different curves in this space, and the exponents which determine the curve are generally a function of the physical parameters of the basin. So our question is, if we look at this within our integrated model where we can control, where we can see everything that's happened with recharge, ET, and overland flow, can we understand how important groundwater surface water interactions are to this if we're violating the no storage assumption? So here along the top of this map, I'm showing our water balance is ET plus outflow plus recharge, so any exchanges you have with the groundwater and surface water. And this is a map just showing the overland flow fraction that we get for our 1-year simulation. And on the right, you can see a plot showing the overland flow fraction versus annual precipitation. And these are colored by aridity. So as in our wetter parts of the domain, of course, we have greater overland flow fraction as a function of our precipitation. What's interesting about our model is that because we're simulating all of the groundwater and surface water, we can directly calculate all of the exchanges that are happening between the surface and the subsurface. So here's a map just showing the groundwater surface water exchanges. And the point of this is to show that we have a 1-year simulation and we know that we're violating the assumptions of the Boudico hypothesis. So we know that we have changes in storage occurring, but because we're in a modeling framework, we can fully quantify these and account for them. Okay, so this is what our results look like if we plot our ET fraction versus aridity. So you can see there's a lot of scatter, but we are generally following this Boudico framework. But what you can see is for each point, so every point in here is a subbasin of our domain, so we can divide it into about 30,000 subbasins. I'll also point out that this is showing for the whole domain, so if I actually split this out by individual watersheds, I could show you that we follow these curves pretty closely once you get homogeneous regions. But for now, this is the whole domain, and for any point, what you can do is you can calculate the exponent of the curve, which I've shown the equation for down on the right, that would get you to this point. And then we can evaluate the impact of recharge on where we're falling in this space. So this is a figure on the left showing the relationship between the exponent of that curve and the recharge fraction, recharge divided by precipitation, for a subbasin. And so what you can see is that there's an inverse relationship, that when we have greater recharge occurring, we have smaller curve numbers, and that's what I'm showing here on the right. So you can just think of these curves moving further away from the upper limits of the system. And this actually has really big implications spatially. So here's 2 maps. The top one shows what our curve numbers would be if we take our recharge and adjust for it before we do the Boudico calculations. And there's a couple of ways to adjust for it, and there's several papers on this, but I won't get into the details. But so we take into account the fact that we know what our groundwater surface water exchanges are, and we adjust for them, versus on the bottom, if we just plotted our ET fraction versus aridity without taking into account that we did have storage changes occurring. And so what you can see is that we get really different spatial patterns, especially in the western part of the domain. And this is because recharge is basically, we have water going from the surface into the subsurface, which is shifting the limits of the system. So that's what I'm showing in the bottom right there, so that there's less water available to evaporate. So we have systematically lower curve numbers if you're not adjusting for them. So the point of this is not really to put forward the map at the top saying that this is our prediction of exactly what the shape parameters should be for each of these subbasins, because obviously this was just done over 1 year, but to demonstrate that recharge has systematic effects on this, and that it can change the spatial variability that you see in points. And so in a lot of cases where we're using Boudico analysis, it's places where we're data limited, so odds are if you can't measure ET, you also don't have a good way to estimate storage changes in your basin. But if we know systematically how storage changes would affect basins, then it's pretty easy actually to just calculate the uncertainty in your storage changes and add this into the variability when you're comparing points within Boudico space. Okay, so the point of those 2 examples was just to illustrate that lateral flow can influence large-scale land energy and overland flow partitioning, and that we can use integrated models to help diagnose this behavior. So the last thing I want to talk about is using this to look at human impacts on hydrologic systems. So for this, I'm going to focus on groundwater depletions. So I mentioned before that we started with a pre-development simulation. So our steady state simulation was just using long-term average precipitation minus evaporation to get a steady state groundwater configuration. Of course, we know, though, that in the U.S. in the last 100 years, there's been significant groundwater pumping. The figure on the left from Conoco et al. Shows the total depletions in the black line. You can see that we've lost about 1,000 cubic kilometers of storage from the subsurface since from 1900 to, I think this goes to 2008. I don't think that line is exactly leveling off at this point. And of course, you can see down below, we have that for major split up by major aquifers. And this trend, of course, increases whenever we have a drought. So I wish I had a figure for the most recent California drought here, but this is just showing the Colorado Basin for the drought in 2012 to 2014, where we know that groundwater storage decreases when we have surface water storage. So the question is, how do these storage losses impact our system behavior, or do these storage losses impact our system behavior? So to do that, we applied net groundwater depletions from 1908 to 2008 from the Conoco study to our pre-development simulation. Actually, the Conoco study just has estimates by aquifer, so we used his estimates by aquifer, and then we used a paper by Yoshiwada, which estimated the spatial distribution of pumping to come up with this map where we have spatially distributed groundwater depletions. So we take these depletions and we apply them to our steady state simulation. And we have now a second year of simulation. So we had our pre-development simulation of water year in 1985, and then after doing additional spin-up, we do another year where we have exactly the same thing, but now we have less storage in the subsurface. So 1,000 cubic kilometers of water taken out, actually a little less than that because we're not covering the whole domain. So same thing though, we use historical observed meteorology. We're not applying any of the irrigation at this point. We're just looking at the impacts of what happens when we have less moisture in the subsurface. So what you can see here, this is the overall storage decrease for some of the major river basins. And what you can see, the black is the baseline scenario and the orange is the pumping scenario. So of course, what we expect to have happen, our total storage decreases in all of these cases because we've taken water out. The total storage decrease is a function, of course, of the map of where we actually had pumping occurring. You can see, though, that even as we're decreasing the storage, we still get pretty much the same annual cycle in these basins, although we do have some that are gaining and losing, and we can look at this at much higher resolution, too. So the question is, what does this mean for land energy fluxes, though? So on the left, I'm showing the change in ET versus the change in water table depth. And here I'm showing just one major river basin, so just plotting it for the Missouri. And I've shown it for 3 different snapshots in time, so for January, April, and July. So you can see, first of all, if you just look at the figure on the left, is that the change in ET is much more sensitive as we move into the water limited season. So in January, the change in ET between the 2 simulations is really small, but as you move from April to July, the changes increase a lot. But we still don't really have a really clear relationship between the change in ET and the amount that we've taken out, the change in water table depth. Conversely, though, if you look at the relationship just with total ET and water table depth, we see this relationship that we expect to see, where when we have shallower water table depths, ET is inversely correlated to water table depth, and then when we have deep water tables, ET is low and not strongly correlated to water table depth. And you can see here the inverse of the first plot, that as we move into the water limited season, the impact of water table depth is more significant on our land energy fluxes. So in January, we have relatively low ET and a weak relationship with water table depth, but as you move into July, we have a much clearer inverse relationship between ET and water table depth and higher ET overall. So when you consider the difference between the first plot and the second plot, what you expect then is that really the change in ET that we see isn't a function of how much water you've taken out as much as it is a function of where your water table was to begin with and how sensitive, whether you were in a sensitive area or not. So this is the figure on the right where you can see that we have the change in ET versus water table depth. Again, more sensitive as you move into the summer months, and we have a positive relationship between the change in ET and water table depth where we had shallower water table depths to start, and we have less sensitivity where we had deeper water tables to start. So this is just illustrating the trade-off between water and energy controls on land energy fluxes and how groundwater configuration can play into these and how we can have different sensitivities to human activities based on what our groundwater configuration is to start. So yeah, the point of that is just to show that surface losses decrease surface water availability. That's what we expect and what we've seen in a lot of previous studies. But then when we look at it within an integrated framework, we can see that the sensitivity to pumping stress varies with groundwater configuration. And so this is a case for showing that we really should be including these integrated models with human impacts if we want to fully understand the ways that humans are operating within these natural systems. Okay, so I've covered our steady state simulations and then the transient simulations we've done with ParFlow CLM. Of course, as I was emphasizing in the validation part of the talk, really we're trying to learn from all of these model development steps to keep making these models better, both by expanding them and improving our inputs and improving our process representation. So moving from our domain, which is currently a box, which is 6 million square kilometers, we're pushing out to the coastlines and also coupling to atmospheric models like WRF so that we can simulate from the bedrock up to the atmosphere. And then thinking back to what we have learned through our model validation activities of our sources of bias of what we can really improve on. And I think that some of this is really a community effort to try to improve things like our climate forcings or our subsurface parameters. For our modeling efforts, we're currently working on improving our subsurface representation, so adding more layers, having the model go deeper, incorporating groundwater pumping and other management activities. So I showed you that we're working on developing our groundwater where we've included groundwater development just in terms of storage losses, but with ParFlow we also can simulate water management activities, so we could have things like irrigation and pumping that's responding to subsurface stress. And then, of course, coupling to the atmospheric processes. I showed in our snow simulations that one of the biases we have in our SWE is from the climate forcings we're using. So if we start coupling in our atmospheric processes, we can start to potentially do a better job of that too. And I think the point of this is to really figure out how we can better answer the questions that I started with. So I think the first question, does improving groundwater representation help us get the right answer? I think there's a lot of indications that the answer is yes, and that we need to figure out how to handle groundwater in these really large-scale models. But the question, because we know it's really computationally intensive, are where and at what spatial scales, and how can we do it most efficiently? And then, of course, what is the best way to parameterize these really large-scale models? Because it's, of course, always a challenge when we need to get high-resolution data that is spatially distributed. And then I think also figuring out how we can incorporate smaller-scale process understanding into these large-scale approaches. Even at 1 kilometer resolution, of course, we know that we're coarse relative to other processes. So how can we best incorporate subgrid heterogeneity? And if we're going up to larger scales, what do we do then? And really to work on evaluating our models so that we can make sure that we're getting the right answer for the right reasons. And with that, I think I'm done, and I'll ask for questions.
Okay. Thank you very much, Laura, for that talk. We can all clap. So be sure to chat your questions. We have a bunch of questions that have come in already, and I'm going to moderate them, of course, as I have every week. So the first question, Laura, is if you could, or questions, if you could briefly summarize and provide a little bit more input on the boundary conditions particularly the surface and groundwater boundary conditions, and the initial conditions of groundwater heads in the model.
Okay, let me just see if I can go back. Okay, so we are using a terrain following grid formulation, so that means the bottom surface of our domain contours to our land surface, and we have a no-flow boundary along the bottom of our domain, and we also have a no-flow boundary along the edges of our domain. So for most of the water basins we care about or that we've been focusing on, our no-flow boundaries on the edges is not an impact to our results. So you asked about the boundary conditions on the edge and the bottom, and our initialization, we started our model completely dry, and then we had that long-term average precip minus evap recharge forcing that we applied to the upper boundary of the model until we achieved a steady state groundwater configuration. And then you asked about the groundwater surface water. So we have a free surface overland flow boundary condition. So basically what happens is in the model we're solving Richard's equation in the subsurface, and if we have ponding that occurs, so we have a head that is above our land surface, then we switch from solving Richard's equation to solving Manning's equation with the kinematic wave approximation, and then we are simulating overland flow. Was that all the parts of it?
I think that's all the parts. That was very comprehensive. Thank you. So there's another question from Amy Rice that says, in addition to thanking you for the talk, wants to know how deep the model is and how deep the unsaturated zone is in the model.
So our model is 102 meters deep everywhere because we have the terrain following grid. The unsaturated zone is variable. We don't specify in advance where the unsaturated zone is because we're solving variably saturated flow everywhere. So that's spatially variable.
Okay, great. The next question is, all right, I have to do this one. So the first question starts out with claps, meaning the virtual applause. And the question is, how do the parflow streams, so the streams that come out of the parflow model, compare to observed or mapped streams, such as in HD+, and then are variations in perennial or ephemeral streams represented in the model?
Okay, so this is our map of streams in our steady state simulation. It looks a little different for the transient simulation. So for parflow, we don't actually input topography, we input topographic slopes. And at 1 kilometer resolution, we have to do some pre-processing of our topography in order to make sure that at that resolution we end up with connected drainage networks. So we use the A-star algorithm to ensure that we have all of our drainage networks connected before we start. But still, even so, that gives us connected drainage networks, but we can still have deviations between our river network and the NHD plus river network. And we've done a lot to look at this. So we have all the 3,000 USGS stream gauges that I showed you that we did comparisons to. So for each of those stream gauges, we mapped it to we first of all just threw it on our grid and saw, where it lines up on our grid. And for the most part, the gauges line up really well with where our rivers are, which would make sense, for the large rivers, the topography is fine. But then, of course, with a lot of the smaller rivers or where we have differences in where tributaries are coming in, we can end up with stream gauges that we see don't line up with our river network perfectly. And so we've gone through every single one of the stream gauges that we compared there and adjusted it to make sure that we're actually falling on the stream gauge, and identified locations in our DEM where we end up turning something a slightly different direction or something like that. So there are definitely differences between the two, and there's a lot that goes into topographic processing and coming up with good DEMs at this resolution. I think there was a second part of the question. I don't remember.
Yes, so the second part of the question was about stream consistency, perennial versus ephemeral streams.
Okay, yeah, so I mean, we have both of those for sure. Again, because we're not specifying, specifying river cells. We have rivers that can form and disappear, and we can see also in our groundwater pumping simulations, I didn't show this, but we have perennial streams that can disappear as we start pumping groundwater. So that's a very dynamic interaction within our model.
Okay, great. So a lot more questions here. I'm parsing them. A lot of detailed questions, Laura. Sorry, people are really interested in the details of the simulations. Okay, so this one is from Todd Rasmussen. Todd asks about EPA uses the drastic procedure to quantify groundwater vulnerability and pollution. And the question says, it seems like you have all the necessary information to implement this. And the question is, how do you see any difficulties, or how would you extend this model to start to think about water quality, pollution vulnerability, as opposed to just flow of water?
Sure. So I'm not familiar with the method that was mentioned in the question, but we've added particle tracking to our par flow simulations, not with the groundwater pumping, but to look at residence time. So I think that if we're going to look at pollution, if we had good information for the loadings, that this would be a really good approach to look at contaminant transport and the risk of different surface water bodies to pollution in the subsurface. So I'm not really sure. I guess how we would expand it would be to add particle tracking to our two simulations where we're also including contaminants. I'm not sure specifically.
Well, I think the person who asked the question can follow up too if need be. But yeah, definitely. Okay, so this is a multi-part question. I'm going to break this out into pieces. So the first question is, how would water management practices, both water resources and agricultural, be incorporated into the modeling in the future, and I guess beyond what you've already showed? And would there be additional, data sets that would be needed to implement this?
So I think that it really depends what you're trying to achieve with the water management modeling. I think that if we're trying to do it at the scale of the continental U.S., we have to have ways of doing it that we're not going to do it the same way that you would for building like a watershed model for your local system, where you're going to take into account every single diversion and water right and all of the complexities that happen within local water management. So I think the way that we implement it for like the continental scale approach is we need information on how people make decisions. So when they decide to irrigate and why, and then we can implement things like moisture-dependent irrigation or deficit irrigation into the model in a really systematic way where we can apply it. We can just make assumptions about how people are making decisions for like groundwater pumping and irrigation. For the major surface water systems, we need to implement reservoirs into par flow, but it's really easy within the model to add things like sources and sinks. So we can move water around really easily. And for some of the surface water, the major surface water systems in the US, I think that's probably the easiest way to transport water within the model. I guess maybe like a less detailed answer is yes, we can add surface water diversions to redistribute water on the surface. We can reroute water just by taking it out and putting it in other places, and then we can add in decision makers who decide whether to pump and irrigate, and we can also add in decision makers who are deciding whether to divert water or not. Probably a more complicated step would be to like couple it to something like a decision support system where you have all of the water rights, you know, specifically for like the Western US. That would be like the next level of complication, which could also be done depending on how you couple things.
Terrific, thanks. So I'm going to jump out of this multi-part question and jump to a really related question by Steve Burgess. And Steve asks, what's the estimate for a time frame for when you might be able to do that? So for example, if you wanted to include water rights and really make this link to like a societal decision support tool, what's your time frame for when this kind of model might be appropriate for that sort of framework?
That's a really excellent question. I would say that's like a multi-year undertaking, but it would depend on the size of the army of grad students who were helping and funding. But I don't think that's like a 10 or 20-year goal. I think that's probably a less than 5-year goal, but maybe I'm optimistic.
Okay, and then there's a lot of other follow-up questions on more detail on input layers and data, so DEM soil, land use that were used, how plant root zones are represented, and if there's, I guess, maybe kind of review that.
Like this slide?
Briefly. Yes.
Okay, so on the left there, that's our land cover type. Shoot, now I can't remember the name of the data set that came from. Maybe the National Land Cover data set. But it is, if you look up that the paper, it's cited in there for the GMD paper of the development of this model. So basically, we just assign every grid cell to a land cover type, and then within CLM, we have all of the properties of that land cover type. So everything that's like savannas has the same wilting point and all of the parameters you would need to input into CLM for it. So we assign every grid cell one land cover type. The soil units come from the USGS, and then for the deeper geologic units, we have this map from Tom Gleason, which is basically hydrology. He mapped permeability, and so we used his map as a guide for the spatial variability, but we adjusted the variance and basically this is also well documented in that paper, but basically we adjusted the actual numerical values of the Ks we would use that would make sense for our 1 kilometer resolution model. And what were the other inputs that they asked about?
I think you've covered most of them. Oh, and then land use or anything like that, if land use is in the model.
Yeah, so we're not, in this pre-development model, we're not doing any like ag land use or irrigation or anything like that. So that's really the next step now that we have the simulation that includes groundwater storage losses, is to also include irrigation in it.
Terrific, thanks. Okay, and then last question is a big picture one, and that's sort of where do you see this going in the future, and particularly as the fourth of the series, the last talk of the series, and what sorts of new or important insights can these large-scale models give us?
Okay, so I guess where I see it going in the future is obviously expanding out and connecting up to other processes, and I think one of the big goals is to try to inform all of the global modeling that's already occurring with like GCMs and Earth systems models, and to try to, as a hydrologic community, have more input into what's coming out of those models and see if we can improve the representations of terrestrial hydrology in that in order to better forecast what's going to happen to our watersheds in the future. Because I think a lot of times now we are taking information from GCMs and then putting them into hydrologic models, but really trying to connect those together. I think that we could get better information about non-stationarity in watersheds if we really start considering all of the interactions. There's two parts to the question. where is it going, and
where is it going, and what are the unique things that integrated models can teach us or show us?
I think the unique things that integrated models can teach us and show us are the connections that if we treat our systems as separate components, like if we treat our surface water separately from groundwater, we can miss things like feedbacks between groundwater depth and land energy fluxes. And so I think anytime we're integrating it, the point is to be able to generate feedbacks between all of the systems that we're connecting. And I think one of the questions that's still outstanding is to really understand when those feedbacks really matter, because it is more expensive to do an integrated modeling approach. So to use these tools to understand where do we really expect our systems to be most sensitive, and where do we expect to really need to capture non-stationary behaviors if we have things like land cover change occurring. We need to be able to simulate that within an integrated fashion, because a lot of the parameters we might use in separate models might not be relevant in the future. So I think there's a lot of things it can do, and I think we actually still don't really know exactly what we're gaining and where it's most important and why, and that's one of the questions too.
Terrific. All right, well, let's all thank Laura one more time, and thank you all for great questions and attendance, and of course, thanks to all four of our presenters. So look for communications from CUAHSI on the next Cyberseminar series. Thanks a lot, and bye.